Area between curves is actually really easy. It's not hard. You can memorize the formula if you want, but the logic is really straightforward. And I'll show you where the logic comes from and why it's also easy as well. So, let's take this as an example. Let's say I gave you a curve like that. Okay? And I ask you, I want you to find the area between, and I'll color it in blue now, between 1 and 2. Okay? If I ask you to find the area of this curve, and I'll call this curve f of x, how would you find the area between 1 and 2? What would you have to do? It would antidifferent between 1 and 2 of f of x. So what you would write is you would say to find the area is the integration between 1 and 2 or whatever the function is. It could be an exponential, it could be a log, we don't care what it is, times dx, right? And you use your fundamental theorem of calculus and you do definite integrals to find the area between 1 and 2. True? Okay, so that was under one curve, the area under one curve. Now, if I gave you, and I'm going to draw another color, so hopefully the coloring will make a difference for you here. What if I gave you another curve that looked like this? Okay? And I ask you to find, okay, the area, whoops, same thing, I want you to find the area between 1 and 2, which I'll color in green here. Okay? Like this, and I'll call this g of x. So I've color-coded it. I want you to find the area of the green section, so the area under the curve of the green graph, which is g. So the area of g of x between 1 and 2, what would you do for this case? How do you find the area of the green shaded region? What would you do? You do the exact same thing, because that's g of x is between 1 and 2. To find the area under that green graph, you would say, well, it will just be anti-derived between 1 to 2 g of x dx. That will give you the area under the curve of g of x. So it will give you the green area. Now the cool thing here is, what if I wanted you to find, which I'll color in orange now, the area between the red curve and the green curve from 1 to 2. Logically, how would you find that answer? Just a logical answer. How would you find that, Daja? Yeah, that's all you're doing. You're literally, all you're doing is you take the large area, which is the blue take away green, to give you leftover orange. True? So the theory, the area between curves, they'll give you this formula, and I'll show you the formula later. And you don't have to think it, because logically it made sense. All you had to do was find the bigger area minus the smaller area, and it'll give you the area between it. So in this case here, if you were to find out the area between these two curves from 1 to 2, all you had to do was you'd literally say it'll be the integration 1 to 2 of f of x, because that was the red graph, take away the area of 1 to 2 of g of x dx. And what I just gave to you there is the formula for the area between curves. The only thing that you have to realize is f of x has to be the bigger area. Now, how do you know if it has a bigger area? What's one thing that you're going to look for to know that it has a bigger area? How did we know that blue was going to be the bigger area? It looks big. So what makes it look big? That's a key word. You're right. It looks big. But what makes it look big? What on the graph will determine whether it looks big, besides the fact that I drew it? Because I'm using something to be able to draw it. What am I looking for? Your x and y's. And to determine which one has a higher area, it's dependent on the y values, because that's your height, that's your y values. So the one with the graph with the larger y value, that's going to give you a larger area. It's a top area. So the top curve minus the lower curve is what they call it. So they normally say in your formula, they'll say, this is the upper curve minus lower curve. will give you the area between the graphs. Does that make sense? Okay, so that's all it is. That's the formula for it. Instead of 1 to 2, they call it A to B. So between A to B, and they'll simplify that formula down to something like this. They'll do it like this. They'll say integration of A to B of f of x minus g of x, because remember, you can write it separately or you can write it together, d of x. And that's the formula for the area between curves, which really just means this. And you didn't have to memorize that because it was logical. You could find the area of one curve, you could find the area of a second curve. Well, logically, between it, you just had to take the larger minus the smaller, and you get the ones in between. Now, there's a cooler thing about this as well, which comes up in the exam. And this normally most students don't do well when it comes to their multiple choice questions. The other thing that's really cool, not only when you're finding the area between curves, it actually now doesn't matter where it is around the x-axis. You see, when we did, I'm going to move on to the next page. When we did area between area under a graph, it mattered when it was below the x-axis. So if I had a curve that was like this, it mattered whether it was above or below. You would have a negative area, you have a positive area. But let's think about area between graphs. Why is it cool that it doesn't matter? So let's think about this. When you're finding this area here between two graphs, and it comes up in your exams often, your tendency is that you'll feel, oh no, we've got it below the x-axis and I've got above the x-axis. It becomes tricky. But why is it that when it comes to area between curves, it doesn't matter if it's below the x-axis? You just need the upper curve minus the lower curve. Can someone explain to me why we don't care whether it's below the x-axis or not? Yes, that is true, but I want you to explain to me more of a logical sense. That is true on an algebraic sense. That's what Daj is saying. I'm thinking more, if I took this graph, okay, whatever this area is, this area doesn't change. When I shift this graph up, okay, if I shift the graph up to, let's say, plus another 10, right? If I move the graph up by 10, what I want you to see is if I shift the graph up by translating it, the area between the two curves is still going to be the same. If I translate it down, it's still going to be the same. Nothing changes. The area stays the same. If it's 5, it's going to be 5 units all the way. It doesn't matter where it is. True? But it does matter if I didn't have a second curve. If I had a graph that was, wait, let me just remove all the ink now. If I had a graph that was like this, okay? Between 0, for the positive area, that's let's say 5 units. But if I shift it up, it does make a difference, because if I shift it up, it's now getting a larger region. True? But when you have two curves and it's enclosed by them, it doesn't matter where you move it. It's always going to be the same. So that's why it doesn't matter if it's below the x-axis, above the x-axis. You can pretend it is above the x-axis. And you take the upper curve minus the lower curve, it'll always be the same. The problem is if you didn't have the second curve, then as you move it up and down, it does change the amount of area. You have either more area or less area relative to the x-axis. And that's a cool thing, because in the exam, you're going to get a multiple choice question where they will give you a graph and they will not tell you to translate it or move it, but they'll give you a graph that is above the x-axis by a certain amount, and they say, find the value. And because it's a multiple choice question, you don't know what the function is. You're not meant to know what the function is. You're meant to know that the area is the same. And you're meant to be able to say, all right, well, I'll just double this, or if I move it up or down, then you choose the correct answer for that, because they'll give you an f of x type graph. They won't give you the actual function. But you're meant to understand that the area between two curves will not change. It will just consistently stay the same as you move left to right, but it does change if it's just one curve. How's that feel? Pretty good? So that's on the theoretical sense. We haven't done an example yet, but that's the theory. Okay? So all of that, everything that you're seeing here is what I was trying to describe just now. F of x, upper curve minus lower curve. You can separate those two. That's what they're trying to say there. Okay? Now, that if you're just trying to read that there, that just means f of x has a larger y value than the second graph, which is g of x. Hence, that's the upper curve and that's the lower curve. Okay? Now, let's do an example, just to get you to get a feel of it. Okay? Now, remember I said methods is all about visualization. The better you can visualize the graphs, the easier it is to do the questions. So if you have a look at this, it says calculate the area of the region enclosed by the curves. You've got x squared plus 1, and you've got y equals to 4 minus x squared. And it's between -1 and 1. Now you already got the formula. You got interval between -1 to 1, f of x minus g of x dx. You've got two curves. So the only way that you're going to get this wrong is if you get the upper curve wrong. So the best way to do it is visualize. Now I can tell just by looking at the graph, I can tell which one's going to be the lower graph and which one's going to be the upper graph. Which one is the lower and upper? Yeah. See, it's a quadratic graph. So if you think about it, this is an x squared plus 1, up 1, and it's a smiling graph. And if you draw this one, it's this is a frown graph, or like a reflection in the x-axis, and it's up by 4. Up by 4. 4, 1. So clearly, you know this has to be the 4 minus x squared graph, and this has to be the x squared plus 1. So if you want to find the area between the two curves, it has to be, upper has to be the 4 minus x squared, which is over here, minus g of x, which is the x squared plus 1. Okay? And now we put them both together. That's easy to work out now. We've got -1 to 1. I've got 4 minus x squared. Subtract. Now every time you subtract, I encourage you to use your notations to put brackets so you don't make the mistake. So I'm doing subtract my lower curve, which is an x squared plus 1 dx. And this now gives me -1 to 1, 4 minus x squared, minus x squared again, and then minus 1 dx. So you can simplify this down to -1 to 1 of, what's that? That's 3 minus 2x squared dx. And that's an easy problem to do now. So that was just your exercise 11E, definite integrals. Anti-diff using 11B, okay, power functions, using your power function rule. Anti-diff, sub in 1, sub in -1, subtract 2, and voila, you get your area between the two curves. So the only hardest part there was to know which one was the upper curve and which one was the lower curve. Cool? All right. So that's your exercise 11I. The next session, I'm going to show you average value function. When students do this in the exam, they will confuse between, or they forget, and I hope to explain it to you that it's one of the easiest ways, one of the easiest things to do. It's one exercise, one simple skill, average value function. You'll confuse it between average rate, average value. They're two totally different things. Yeah? And examiners know students mix those two up because there's one formula, it's in your formula sheet as well. Most students don't realize that's the average value because they don't know what the average value means. And I hope to explain it in the next lesson so you know what average value is, and that's different to average rate. Average rate is differentiation, average value is anti-diff. Okay? They're two different meanings as well. Okay? But I'll leave it there. You guys can practice on 11I. That's just area between curves, and do this in your CADs as well. Remember to practice your CADs work. But that's a really good one for exam questions. Exam 1, this is a nice one that comes up. And let me just check. I think there was, I don't know if I had exam questions in this one actually. Some exam questions. Did I have an exam question? Yes, I did. All right. I'm going to get you to practice just the first few questions, and now I'm going to do this example with you. This is just one of those problems where you, instead of finding the area with the x-axis, you can find the area with the y-axis. and that normally comes up in the exam. So for the final questions they'll have the swapping of the variables. These are a good one to try. If you're done Special, you should be able to do this one. If you haven't done it before, then just wait and I'll go through this one with you. Jun's here. Jurity's here. I thought I saw something else. Who else came in? Ciao. Okay. So not the head. Oh, why? That's not way out. That's the bad. Why up? This person's compliant. Like, so that's what like the second like times a week and all the areas together. Given that.
我给你写算了，我期待写。开走，你走。
Give you about another 6 minutes, and then we'll go through example 30. Example 30 is only tricky because of C. Because we don't know how to antiderive a log. We know how to antiderive a 1 on x, but we don't know how to antiderive a log unless you're doing spec. But we don't know how to antiderive a log. Alright. Let's see. Liffey. Michael. Who else was in here? Does that make sense? 4 plus 7 is 11. 4, 5, 6, 7, 8, 9, 10. Someone else. Who did I miss out? Steph. Yes.
In our last calculation for calculation or differentiation doing, we want to make sure that the last result is the whole thing, not two separate articles. Like for example, question of this, and also maybe something like one taking flow to another dot.
Okay, that's fine.
That's two terms. We have to something.
No, that's fine. Because that's a constant term. And log e is not a fraction. It's when you have two separate fractions, then you must combine it as one fraction. Oh, no. I've only taught spec 1 year, so I don't know. I don't know what year 12's like. Two more minutes.
追求不同方式减面的这个。Yes. Appreciation of my growth.
3 times exchange. 3 times x. I think the application it's something that you don't really care about. When you're driving speed, whether you are driving from west, 60 kilometers per hour west, 60 kilometers per hour east, but mathematically, it doesn't make west, wow. Probably that this way, that way, this way, 20 kilometers that way. You add them, once it happens, once. What you want is just the whole values. So you want 160 that way, 30 that way, 20 this way. Overall, what's my last speed? Yes. Another way of gain or lose, losing doesn't matter. I'll make it 3. So there are certain cases where you don't want a sign. The sign is a tool for us mathematically to tell us the direction. All right, so let's do this problem. Example 30. For the function, so A, you're going to find the inverse, so hopefully chapter 7, exercise 7b, if you haven't done it, have a look at chapter B again, that's your inverse functions. Swap the x and y's. Revise chapter 5, log and exponential, so that's a log base e, so exponential both sides, cancels out to log e. You got e to the x, and then y, which is y equals to e to the x minus 1. This is your inverse function. So I've redefined it, I've answered the question, and they've graphed it. Okay, that's not the main skill. This is just the preparation to the question. Now B says find the exact value of the area, okay, and you want the area of the inverse function with respect to x between 0 and log e of 2. Okay, so we're doing B. If we were to do this problem, we've got e to the x minus 1, we've got the function already, and we can antidiff this because we've got the rules for it. We know the antiderivative of e to the x, which is e to the x. Antiderivative of 1, which is x. Okay, so we know how to antiderive that. That was pretty straightforward. We can say what it is. Find out between 0 log e of 2 of e to the x minus x. And now you can do definite integrals, sub in log e of 2, and then sub in 0, and you can solve. So that's easy to do. From here, we can work with our exponential equation. So log base e of 2 minus log e base of 2. Subtract, now sub in 0, so e to the 0 minus 0. Yeah? So that ends up being minus 1 Base e, log e cancels out, so that's 2 minus log e of 2. And then 2 minus 1 becomes 1 minus log e of 2. Okay, so that was easy. C is the question I want you to think about. How do I do C? Because C, which is, I'm actually doing integration between 0 to 1 of log e of x plus 1 dx. The problem is I don't know how to anti-derive log e of x. I've given you a rule for that one. All the rules we've done power rule, chain rule, we did anti-diff of sine of x, cos of x, anti-diff of e to the x, and anti-diff of ax plus b to the power of r, where r is negative 1 or r is not negative 1. But never did I give you a rule where I said anti-diff log e of x. So how do we do this one then? You can type in your calculator, yes, but I want. And why do they give you the precursors? Why do they do a preparation? A, B, obviously has to do something with the inverse. Substitution. Substitute what though? What are we doing? Can someone explain to me why we do that too? Anna, what are we going to do?
That section 1 and x is integration. We've already got the inverse function. So we can use that and integrate with respect to y. And we've got the points 0 and 1, so we can sub in 0 and 1 to the function f of the inverse of x to find what the y coordinates will be. And then we can do that integration f of the inverse of x to get the y coordinates.
Very good. So, what we're really saying on a visual basis, so you were kind of lost by what was explained there. I'll draw it for you. This is what we want, and I'll color it in green. This is what we want so far. From 0 to 1 of f of x, this is the area under the curve that we want between 0 and 1. Okay, and that hasn't changed. Our goal still is the same. We want this, but we haven't got that yet. The problem is we don't know how to do this unless you use a calculator, right? Alternatively, it doesn't have to be with respect to x, because the inverse function is technically exactly the same. It's a mirrored image. It's a mirrored image along the y equals x line. So because it's a mirrored image, this area that I'm looking for, it could also be replicated on the y-axis. Why do I want the inverse function? Because the inverse, I can integrate that. That's something I can do. So that's good. I can do this by hand. The problem is, what is my interval if it's between 0 and 1 on your x-axis? What's the interval for your y values? Okay, that's what we don't know. So, what I'm trying to say, I'm going to color in orange here. We want an equivalent distance, an interval from A to B for the y values to have the exact same area that's replicating in green. So wherever it's green, I want the orange. The interval currently for green is 0 to 1. What I don't know is A to B. How do we find A to B? We've got our function over here. See our function over here, this is your inverse function. That tells you the y values for your inverse if you know what x is. But you do know what x is because they told you it was 0 and 1. They said 0 to 1. So 0 to 1, we want to know what is the corresponding x and y values for. Okay? And so if you sub in x equals 0 and you sub x equals 1.
We need to solve it, but it's a reverse. If it's a mirror image, but the y should be 0 as 1.
Wait, that doesn't make sense.
Yeah.
Oh, because if I do 0 to 1, I'm actually getting this point here.
To the power of 1 plus 1, what does that even mean?
Yeah, wait, hold on a second. We want 0 to 1, so it will be an inverse function.
It's a mirror. Whatever the x is, should be on y.
Yes, you're right. Yes, sorry. It should be 0 to 1 of e to the x minus 1. But I thought... Let me just think about this for a moment. and whether that's true for every time. Yeah, no, you're right. Yeah, because it's a mirrored image, in our case it's 0 to 1 here, so from here to here has to also be 0 to 1 to do it. So you're really just doing 0 to 1 of e to the x of minus 1 dx to solve them. Sorry? Yeah. Yeah. That's weird. Let me just double check that. It just felt like you had to do, so from 0 to 1 for this curve, that's the distance.
When did you know among directions?